Hey guys, this is 5.2 part 2. We're going to be talking about polynomial functions this time. Alright, so we've talked about polynomials some, but we're going to be talking about specifically their properties when it comes to graphs this time. So let n be a non-negative integer. A polynomial function is a function that can be written in this form. Okay, so I think we all kind of know what a polynomial is. We've talked about them earlier this year. But basically, you've got multiple terms, or it could just be one term, that'd be a monomial. And then you've got coefficients, you've got exponents that are whole numbers, positive whole numbers, and that's pretty much it. It's called the general form of the polynomial function, each ai. So each of these a's just represents a real number, and then the leading coefficient can't be 0, right? If the leading coefficient were 0 here, then that whole term would just go away, so it wouldn't even be there to begin with. All right, so let's recall some terminology of polynomial functions by labeling this polynomial. So first of all, this is your leading term. That's your leading term. This is your leading coefficient. And then that exponent, the 5, is the degree of the polynomial. This last one is called the constant term because it doesn't have a variable attached to it, so it is going to remain constant. And then the last thing I would say is that all of these, remember, are just considered terms. One other thing to mention is that the way that this polynomial is written is in standard form, and that's where the exponents go from highest to lowest. So you've got 5, 2, 1, and this would be x to the 0 if there were an x there. Okay, so that is standard form for a polynomial. Where your terms are written in order of largest to smallest exponent or degree. All right, let's talk about the end behavior of polynomial functions. We talked about the end behavior of power functions in the last video. Now we're talking about the end behavior of polynomial functions. So for any polynomial, the end behavior of the polynomial will match the end behavior of the power function associated with the leading term. And that, of course, is when the polynomial is already in standard form. So really, you're just looking at the term with the largest exponent, and that is the leading term, right? That should be the leading term. And so whatever end behavior is associated with that leading term is going to be the end behavior of the polynomial. The reason is because, well, let's do an example and then I'll tell you why. Okay, so number 3, describe the end behavior of the graph of the function. So first, maybe we want to write it in standard form. Maybe we want to write the negative 2x to the 6 first because it has a larger exponent. And then we would put the 3x to the 4th, the x cubed, and then minus 15. Okay, so we rewrote those in the standard form. Now, I see my leading term is negative 2x to the 6th. So however that power function would behave as x approaches positive and negative infinity, that's how this whole polynomial is going to behave. The reason is because that power of 6 is so large, or just larger than the other powers, it's going to have a bigger effect on the graph than any of the other ones. Just because that exponent is larger, it's just going to pull that function in the direction that it wants to go. It just has a larger pull because it's a larger exponent. Okay, so let's see what that would be. We've got a negative leading coefficient, and we've got an even exponent. The degree is even. And so remember, even means it's going to be in the shape of a parabola, although all of this affects that as well. But the end behaviors are still going to be like a parabola. But it's negative, so it's going to reflect. So it's going to be an upside down parabola. So your end behaviors are going to be like this. As x approaches positive or negative infinity, because this is an even function, it's going to go the same direction on both ends. And because it reflected, you can go ahead and say this, it reflected, so your end behaviors are going to be like this. They're both going to be going down towards negative infinity. So as x approaches positive and negative infinity, f of x approaches negative infinity. All right, number 4. I think I'm going to have to move this out of the way because I'm not going to have enough room. I keep doing that. Okay, maybe that'll work. Number 4, g of x equals 3x times x minus 1 times x plus 4. So maybe in order to see my leading term on this one, I'm going to multiply everything out. So first I'll distribute the 3x. And then we're going to FOIL these two together. Okay, so 3x cubed, 12x squared, 3x squared, negative 3x squared, minus 12x. Let's combine like terms. All right, perfect. So that's g of x. Now let's look at our leading term, because we know that that's the one that determines our end behaviors. This is positive, so it's not going to reflect, but my degree is odd. So that means that it's going to look like the cubic function, like so. So let's write our end behavior. As x approaches positive infinity, so as we move to the right, my graph is going up. So f of x approaches positive infinity. And then as x approaches negative infinity, f of x approaches, well, as I move to the left, it's going down. So approaches negative infinity. Right, identifying local behavior of polynomials. All right, so a turning point of a polynomial, turning point is a point at which the function values change from increasing to decreasing or decreasing to increasing. So basically, you're talking about a vertex. Like on a parabola here, this is a turning point. It's any time where your function goes from increasing to decreasing, or if it were going this way, now your polynomial is going from decreasing to increasing at that point. So those points are turning points. A polynomial of degree n will have at most n minus 1 turning points. So let's say you're looking at x to the 4th. Then it's going to have at most three turning points. N minus 1. Your exponent minus 1. Okay. The y-intercept is the point at which the graph intersects the y-axis. I think we know that. I hope we know that. This is also the point where the input value x is 0. Right? The y-intercept is where x equals 0. So if you're trying to find a y-intercept of any function, you can always plug in 0 for x to find the y-intercept. All right, and then the x-intercept. X-intercepts are points at which the graph intersects the x-axis. The output value corresponding to these values is 0, right? All that's saying is, right, output value, that's just y. Y is your output value. Corresponding is going to be 0. So if you want to find the x-intercepts, plug in 0 for y and then solve. A polynomial of degree n will have at most n x-intercepts. So if you have x to the power of 7, you're not going to have 10 x-intercepts. You're going to have 7 or fewer x-intercepts. All right. So a little information about behavior of polynomial functions there. Here's an illustration of some of those definitions that we just talked about. These are turning points here. It's max and a min, really, but these are turning points. This top one where the graph goes from increasing to decreasing, and this one at the bottom where your graph goes from decreasing to increasing. And then of course your x-intercepts along the x-axis, your y-intercept on the y-axis. All right, so like I mentioned a second ago, given a polynomial function, you can determine the y-intercepts by setting x equal to 0 and finding the corresponding y value, right? That makes sense because you're at your y-intercept, what does x equal? It always equals 0. The y-intercept always has an x value of 0. Determine the x-intercepts by solving for the x values that yield a value of, yield a y value of 0. So your y is going to be 0 for your x-intercept. So you're looking for the x values that make y equal 0. All right, determine the intercepts of the polynomial functions. So for number 5, if we want to determine let's just do in the same order that the definitions were given. So we'll do y-intercept first. You're going to set x equal to 0. So I'm going to have f of 0. Well, 0 times -6 times -3. 0 times anything is 0, so that one comes out to 0. So your y-intercept is the point 0, 0. Now let's talk about the x-intercepts. So for x-intercepts, you're plugging in 0 for the y value, or setting your function equal to 0. So 0 equals x times x minus 6 times 2x minus 3. Now, hopefully we remember back from when we solved quadratics by factoring that if you have this situation, you can set each factor equal to 0 and solve for x. The reason is because if I have 3 things that multiply to give me 0, one of them, at least one of them, must equal 0 in order for that to happen. So either x has to equal 0, x minus 6 must equal 0, or 2x minus 3 must equal 0 in order for them to multiply to give you 0. So just set, if you have your factors and you're looking for the x-intercepts, it's just the easiest option. Actually, if it's already factored for you, you're lucky. But anyways, you will just set the factors equal to 0 and solve for x, just like we did with quadratics. All right, so your x-intercepts are, remember the y value is going to be 0 for all 3 of them. So 0, 0, 6, 0, and 3 halves or 1.5, 0. So those are all of your intercepts for that function. Number 6. This one, let's see, our y-intercept, there's always only one y-intercept or else it's not a function at all, right? It wouldn't pass the vertical line test. But for a y-intercept, you're plugging in 0 for x, so we're doing g of 0. Okay, so 0 minus 0 minus 20 gives us negative 20. So the point is 0, negative 20. Okay, now for the x-intercepts. Plugging in 0 for y, or g of x, just setting your function equal to 0. And here, we can actually factor this to find our x-intercepts. So factor out the 2, your GCF, and now we want to factor this trinomial. So remember, to factor trinomials, you're thinking what number adds to negative 3 and multiplies to negative 10. Adds to negative 3 and multiplies to negative 10. That is going to be 5 and 2, negative 5 and positive 2, so that they add to negative 3. And now we can set each factor equal to 0 and solve for x. You don't need to set the 2 equal to 0 because that's impossible. There's no x involved in that 2, in that GCF, and so since 2 cannot equal 0, that does not give you a factor. X minus 5 equals 0 gives us x equals 5, and x plus 2 gives us x equals negative 2. So you have 2 x-intercepts on this one. They are negative 2, 0, and 5, 0. All right, what conclusions can you draw about the polynomial represented by the graph? So let's see what we've learned today. We have learned about, well, we just talked about intercepts. So let's look at those. We've got 2 x-intercepts. Two x-intercepts. Can't tell exactly what they are, so I'm not going to say what they are. I'm not going to try to guess. We have a y-intercept right there. How many turning points do we have on this graph? So here's a, let me change colors. Here's a turning point. Here's a turning point. There's a turning point. So we have 3 turning points. And so if you look back on the previous page of our notes, we talked about how the number of x-intercepts and the number of turning points can point you towards what the degree of the polynomial would have been. So remember, a polynomial of degree n will have at most n minus 1 turning points. So the degree of this is telling me the degree could be 4. The degree could be 4. Could be something larger than 4, but it could not be less than 4. And then our 2 x-intercepts up here, that's telling us that your degree is at least 2. So maybe I should put that on both. So your degree must be at least 2 to have 2 x-intercepts. Your degree needs to be at least 4 to have 3 turning points. Now, let's think about the things that we learned before that. We talked about the end behaviors. So since both end behaviors are going up, so since as x approaches infinity, positive or negative infinity, f of x approaches positive infinity, this is telling me that this is an even polynomial and that the leading coefficient is positive. Because if the leading coefficient were negative, both sides would be going towards negative infinity, like that. All right. So those are just some things that we can tell based on things that we've learned yesterday and today about this graph. All right, that's it for 5.2.